problems that involve the dependent motion of two bodies connected together through a system of chords. We'll begin with this one. See if you can determine the velocity of the block at B if A is moving downward at 6 meters per second. Well, to solve the problem, we first establish a fixed datum through the pulleys right up in here, and then we locate the end of the cord right here with a coordinate S sub A. And we can specify the motion of the block if we go with a coordinate right down to here. We'll call that S sub B. We can now find the vertical length of the cord, which is changing with time. We would write the position coordinate equation as S sub A plus 1, 2, 3 S sub B, and that all equals L, a constant. If we take the time derivative, we have a relationship between the velocities. Here, the velocity of A is 6 meters per second positive, and when you calculate V sub B, you find it will come out to be minus 2 meters per second. That means, of course, that B is moving upward at that rate. All right, now try to solve this one. See if you can find the velocity of the block at B when A is moving downward at 4 meters per second. Well, here again we establish our fixed datum, and from it we measure the location of the block using this position coordinate. We'll call it S sub B, and we'll measure the end of the cord using this coordinate, S sub A. Now we can write our position coordinate equation. In order to total the vertical length of the cord, we have S sub A plus 1, 2, 3, 4 S sub B equaling L. Taking its time derivative, we have the relationship between the velocities. V of A is equal to 4 meters per second positive, and when we solve for V of B, we get our result, minus 1 meters per second. So the block is rising. Now let's solve a problem that involves two chords, like this one. See if you can find the velocity of the crate when each end of these two chords is pulled down with the velocities you see here. Well, to solve the problem, we'll have to write two position coordinate equations. So let's begin by writing one for this chord. We set up a fixed datum through the three fixed points like this, and then we'll measure the end of the cord with a coordinate S sub B. And then we'll go to this point with a coordinate S sub D. With these two coordinates, we can then measure the vertical length of the cord, which is changing, but is equal to a constant length. We have S sub B plus 2 times S sub D. And this is equal to L. If we take the time derivative, we have V sub B plus 2 times V sub D. And this all equals 0, of course. If I substitute V sub B equaling 5 meters per second into here, I can get V sub D. It turns out to be minus 2.5 meters per second. That means that this point is moving upward. Next, we'll consider a position coordinate equation for this chord. In order to do that, we'll put a position coordinate going here, call this S sub C, and of course another position coordinate down to A, S sub A. Now we can write a position coordinate equation that relates the vertical length of the cable. We have S sub A plus S sub C plus this piece. And of course that would equal S sub C minus S sub D. All this will equal another length, L prime. its constant. Taking the time derivative, of course, you'll see that you get v sub a plus 2 times v sub c, and finally we have minus v sub d, and it all equals 0. But v sub d is equal to minus 2.5. So putting that into here, of course, we'll change the sign of this term. V sub c is the unknown in the equation. V of a, of course, is equal to positive 2. Solving for v sub c, we get our result. It turns out to be minus 2.25 meters per second. That's the rate in which the crate is rising. Finally, we'll consider this one. See if you can determine the velocity of block B, again, using a system of 2 chords. Well, to solve the problem, again, we'll have to write 2 position coordinate equations because we have 2 chords in our system. So let's go ahead and set up our fixed datum like this, and we'll consider first the chord right here. We'll need a position coordinate going down to this point. Refer to that, of course, as S sub d. And another position coordinate going down to here. We'll refer to that as S sub b. Because if we know the motion of this point, we know the motion of the block. Now we have to relate the 2 coordinates to the vertical length of chord. And that's pretty straightforward. That's simply S sub b plus S sub d equaling L. And if I take its time derivative, I find that v sub b plus v sub d is equal to 0. Of course, I can't solve here because I don't know what v sub d is yet. So let's consider the next chord. There, of course, I'll have to use another position coordinate, and I'll go down to here and refer to this one as S sub a. Now I can proceed to write the length of the chord. So here I have the following. S sub b, we have plus this segment right here, which of course is S sub b minus S sub d, and finally we have this segment, which is S sub a minus S sub d. And all of it equals L prime. If I take the time derivative here, you get the following result. 2 times v sub b, we have minus 2 times v sub d, and finally plus v sub a, and it all equals 0. Now I've written 2 equations that we need to solve. Well, v of a is equal to plus 2. And here, of course, v of b is equal to minus v sub d. So if I put that into here, you'll see that minus 4 v of d is equal to minus 2. So v of d comes out to be 0.5 meters per second. And substituting this up into here, we get v of b equaling minus 0.5 meters per second. So b is rising at that rate. Having completed the problem then, we'll end our review.